All right, I have a question here. It's actually part of it is from the lecture notes. The question is, give a recipe for preparing a bicarbonate carbonate buffer solution. The pH is given to be 10.4 and the pKa of the bicarbonate is given to be 10.25, and it's told that you have to prepare 500 milliliters of the buffer. First things first, you can absolutely use the HH equation in this case, and simply say that since pH is going to be equal to pKa plus log of the base divided by the acid, the pH value is given to be 10.4, the pKa value is given to be 10.25. So you can hopefully see that you can determine the ratio of how much of the base and how much of the acid you're supposed to keep. So when you solve this, first you will take the 10.25 on the other side, and so you'll have 0.15 is equal to log of base over acid, and so you can get the ratio of base to the acid, and I'm punching on my calculator as we solve this. 10 to the power of 0.15, I'm getting a value of 1.412. So as long as the concentration of the base, which is the carbonate, to the acid, which is the bicarbonate, as long as that ratio is 1.412, we are set. In this case though, we have been given that you have to come up with only 500 milliliters of the reaction, the buffer. So hopefully you can see that the square brackets, that was molar concentration, which is nothing but moles per liter of the solution of the base divided by moles of the acid divided by the concentration. The volume is the same, and that value is supposed to be 1.414. So hopefully you can see that the molar concentration directly correlates with the moles of the base divided by moles of the acid, which should be in the ratio 1.414. So that's one aspect of it. Now let's say you were given a concentration that sodium bicarbonate is given in, so NaHCO3 is given in 2.12 stock solution, and maybe sodium carbonate is given as 3 molar, and hopefully the ratio of this 3 divided by 2.12 should be somewhere around 1.414. And so you can hopefully see here that basically they're asking how many milliliters of each of these would you need to mix such that the total volume is 500 milliliters. So again, that's a very mathematical linear equation that we are looking at. Let me erase parts of this so I can make room for what I want to do. Suppose that, and I want to switch colors to maybe pink. Suppose I take X milliliters of the base. So X milliliters of base means X times 3 moles per liter, and this is X liters. So the liter and liter will cancel, divided by 0.5 minus X times the 2.12 is equal to 1.414. So your equation has all of a sudden started looking like 3x, which is the moles of the base. And how did I get that? Since I know molarity times volume gives you the moles. Volume is the one parameter that I'm trying to determine. Molarity was given in the question. So 3x divided by 0.5 minus x times 2.12. So let's solve that. Is equal to 1.49884. Of course, you have to go by the sig figs ultimately. So I'm going to minus 2.997x, and then you solve for x. So x is coming out to be 0.2539 liters, or 0.25 liters. And when you subtract that from when you subtract that from the 500 milliliters, you're going to get the amount of acid that you must weigh to get the correct number of milliliters for the acid component. This is base, that's the acid. Understand what I told you in class. The buffer effectiveness can be measured using the buffer range and the capacity. Range and capacity. So a couple of things on that. The Henderson-Hasselbalch equation gives you that pH is equal to pKa plus log of the base divided by the acid, concentration of those. And so if the concentration of the base and the concentration of the acid is exactly equal, then you will say that pH is equal to the pKa, and the buffer will be most potent in that case. But if you don't have these in equal concentrations, and let's say the ratio between the base to acid is 1 divided by 10, that means the acidic component is greater, so acid is more. Like I said in class, it can only be in the ratio 1 to 10 or 10 to 1. That's the maximum limit. So if B over acid, if that is 1 over 10, so we have more of the acid, that would mean that the pH is going to be equal to pKa plus log of 0.1, and this number is a -1, so that is why I say it's plus minus 1 unit of the pKa that decides the pH of the buffer. If the base component is more, so the negative charge is more, in that case the base is going to be 10 and acid is going to be 1, which is the extreme limit, and so the pH is going to be equal to pKa plus log of 10, which by the way is 1, so you can say that pH is equal to pKa plus 1. So anytime you have to determine which kind of buffer to go by, look at your application. I said that umpteen number of times in class. Look at your application, and that will decide whatever is a buffer that's closest within plus minus 1 range. That's going to tell you, that's going to give you the best buffer. So if the question is, let's say, which acid would you choose to combine with a sodium salt to make a solution buffered at, let's say, pH of 4.25 is what you want. Okay, that's what you want. And there are several several buffers that are given. Chlorous acid, maybe that one is at, so there is one that operates at 1.95, there is another that operates at 3.34, there is a third one which operates at 3.74, and then a last one which is at 7.54. So there are 4 different choices that are given for 4 different buffers, and their operating ranges are provided. Hopefully you can see that the closest, or the one that will be within the plus minus 1, will be the 3.74. That will be the closest, so that will be the safest bet to go for this kind of an application. Okay, I want to drive this point across. We have a situation here. Let's say I have a buffer that's made up of a weak acid HA with its conjugate base A minus, and the pKa of that weak acid is 5, let's say. Okay, and you have 2 situations. You have one buffer A that you are using, in which case you have used 0.1 moles of HA and 0.1 moles of A minus, and there's another buffer that you're trying to synthesize, trying to generate, in which case you have more of the acid, less of the conjugate base. So understand, in one case I have equal amounts of the acid and the conjugate base, and the other I do not have those equal. And so the question is, which one will be a better buffer, or how do we go about it? How do we tell that? So realize in this case, since the amount of acid in the second case is greater, the amount of acid is like HA is like 0.18 moles. And one way to determine this, if you can determine the percentage change in the pH when some kind of a strong base is added. So in order to do that, you will be using your Henderson Hasselbalch equation, but you have to see what would happen when that base, when the OH negative is added to this buffer. Hopefully you can visualize that the acid component is going to react with that added base. It's going to give you water, and A negative will get generated. So before you added your extra base, of course, the concentration of the acid was 0.1, the concentration of the conjugate base was 0.1, and you have added 0.01 moles of the hydroxide, so the total concentration later becomes 0.1 minus 0.01, which will become 0.09. On the other hand, the concentration of A minus will become 0.1 plus 0.01, which will be equal to 0.11. So if you use Henderson-Hasselbalch equation for pH equals pKa plus log of the base divided by the acid and plug in the value of base as 0.11, the acid as 0.09, you're going to end up with a value of pH as 5.09. Now, if you were to determine, how this value is going to be different as compared to your original pH, the initial pH. Hopefully you can see that the case where you had equal moles of the acid and the base component, in that case the pH and the pKa will be exactly the same. So we started with a buffer at 5, and now after the addition of the sodium hydroxide it's at 5.09. so the change is by 5.09 minus 5.00 divided by the true value, which is 5.00 times 100. So it's a very negligible amount of change, and as I'm plugging into my calculator, I'm getting a number 1.8%. Let's compare that to the second buffer that we had generated. In that case, if you use the Henderson-Hasselbalch, pH equals 5 plus log of the base is 0.02 and the acid is 0.18. So if you use those numbers as is, I'm getting a value of 4.05 is my starting solution. That's my initial pH. And now if I do the same thing, that upon the addition of the hydroxide, what happens, that hydroxide is going to react with, again, the acidic part, and so your numbers will start looking like, let's make some room here. So before the addition has taken place, and maybe I'll use a different color so you can differentiate. So I'm going to use brown for the solution B. So my initial concentration of HA is 0.18 and the conjugate base is 0.02, and I have added only 0.01 moles of the hydroxide. So hopefully you can envision that after the reaction has occurred, after that neutralization takes place at equilibrium, 0.18 minus 0.01 should be 0.17, which is what should get generated for the HA, and we have additional A minus now. So now if you use your Henderson-Hasselbalch after the addition of the little bit of sodium hydroxide, and you plug in the values, pKa is still 5.00 plus log of 0.03 divided by 0.17, which comes out to be 4.25. And so we started with 4.05, we are at 4.25, so the change in the pH, the percentage change in the pH is going to be 4.25 minus 4.05 divided by 4.05 times 100, and that comes out to be 5%. So understand that in case of the second buffer, in which we did not actually have equimolar amounts of the acid and its conjugate base, that's not it has buffering action. I'm not saying that it doesn't have buffering action, but it's lesser than what it would be if those were completely equal. So I talked about, for buffers, I talked about buffer capacity. I talked about how to determine which is a better buffer. We also took a look at the absolute numbers to determine the recipe of the buffer. I'm going to now move to titration in the third video.